Hi Math 30s. This video is going to be the second part of lesson 2 and it is on something called permutations. One thing I want you to note for permutations is that order is important. So what's an example of a permutation where order is important? It would be a PIN number to, let's say, your bank card. If you had a 3-digit PIN number, and let's say your PIN number contained the digits 3, 5, and 7, how you enter those 3 digits is important. So for example, let's say that John forgot the order of the 3 digits. What are the possible combinations that they could be? So with the numbers 3, 5, and 7, his PIN number could be 357, or it could be 375. His PIN number could be 537 or 573. If it started with a 7, his PIN number could be 735 or 753. When you're entering your PIN to get access to your money, it matters the order that you enter those digits. So a PIN number is actually an example of a permutation. Star this, it says a permutation is an arrangement of a set of elements in which the order of the elements or the order of the numbers is important. Let's look at another example, and we're going to look at a word. So it says list all of the arrangements of the letters of the word cat. So how many different 3-letter arrangements can we make using the C, A, and T? So we could have the word cat. We could have the arrangement CTA. We could have the arrangement TAC, TCA, ACT, and ATC. There are 6 different arrangements using the letters in the word cat. How we would have looked at this in lesson 1 using the fundamental counting principle is we would have said, okay, to complete this task, how many stages would we have? Well, cat has 3 letters, so that would be represented by 3 stages. How many choices of letter can you put in this first stage? Well, there's 3 choices that can go into that first stage. After you place a letter, there's 2, and then there's 1. So there's 6 different arrangements that we could make using those 3 letters in the word cat. This is how we would set it up using the fundamental counting principle. We could write the number of permutations, which is 6, in factorial notation. So if cat has 3 letters, then in factorial notation, that would be 3 factorial. And why that is because we know that unzipping 3 factorial is 3 times 2 times 1, which is equal to 6. There's a general way that we could do this for factorial notation. So let's actually, before we look at the general form, do class example number 5. So it says determine the number of permutations of the letters of each word. So Regina has 6 letters, so that would be 6 factorial. If you type in 6 factorial on your calculator, you're going to get 720 different permutations or 720 different arrangements for the letters in this word. Make sure you're able to also understand and illustrate that using the fundamental counting principle. So Regina, again, has 6 letters, so that would be represented by 6 stages. The number of choices that I could put in that first stage is 6 after I've placed a letter 5, 4, 3, 2, and 1. Kelowna has 7 letters, so that would be 7 factorial. And the number of different arrangements or permutations that I would have would be 5,040. It says use the fundamental counting principle to determine how many 3-letter arrangements can be made from the letters of the word in graphite. So 3-letter arrangements says that we would have 3 stages. The word graphite has 8 letters. Using the fundamental counting principle, if we're only making how many 3-letter arrangements can we make? In the first stage here, I've got 8 choices of letters that could possibly go there. After I place a letter, you'd have 7 and then 6. So how many 3-letter arrangements we could make using the letters in graphite would be 336 different arrangements. Okay, We could write a permutation as follows. So it's going to be n permute r, and I want you to just jot down that what this n is going to stand for is the total number of elements. So for example, the total number of letters in the word. So for graphite, the n would be 8, right? There's 8 elements or 8 letters. How many we're permuting, n permute r. R is how many are we going to permute or arrange. That's going to be the number of stages. So this example here would be, there were 8 letters given, and we're going to permute 3 of them, right? We had 3 different stages. We have a button on our calculator for permutations. So we know that 8 permute 3 is going to be 336, but here's where that button is. So type in 8, go to your math. Remember, everything is going to be under probability, and permutations is number 2. So 8 permute 3 is 336. I just want to illustrate again another example. So let's say you were given 14 permute 4. What this would sort of indicate is we've got a letter with 14, or sorry, a word with 14 letters, and how many different 4-letter arrangements can we have? So this would be 4 stages. So you would set up your 4 stages, and if it's 14 letters in that particular word, we've got 14 choices of letters that can go there. Then 13, 12, and 11. You would multiply those numbers together, and how many 4-letter arrangements you could make from a 14-letter word would be 24,024. Remember, this is how it would be represented in the fundamental counting principle, but on your calculator, 14, math button, permute, and then 4. And we get that same number. What it says is the number of permutations of n different elements taken r at a time can be represented by this formula here. And this formula will be given to you on your formula sheet, but you have to be able to use this formula. So it says use the n permute r key on your calculator to evaluate 8 permute 3, which we did, right? 8 permute 3 is 336. So let's write that down. And then it says verify using factorials. If it says verify using factorials, we are using this formula here because this formula uses factorials. So 8 permute r is equal to n factorial, and n is 8, all over n minus r, which would be, sorry, let me just change this. Okay, so n minus r would be 8 minus 3, close that bracket, factorial. We know that that would be 8 factorial over 5 factorial, and then simplify this by unzipping the larger factorial, which would be the 8. Remember, you unzip until you are able to cancel with a 5 factorial. So 8 factorial could be rewritten as 8 times 7 times 6 times 5 factorial, all over 5 factorial. And then you are left with 8 times 7 times 6, and that is equal to 336. 8 times 7 times 6. Okay, let's look at class example number 6. So it says, in a region, vehicle license plate consists of 2 different letters. So 2 different letters, right? So that means no repeats, followed by 4 different digits. And then what it says, if the letters I, O, Y, and Z are not used, so there's a restriction, how many different license plates are possible? Illustrate first using the fundamental counting principle. So I set up my number of stages. Let's place in our letters. So remember that the alphabet has 26 letters, but I have to subtract these 4. So these 4 letters cannot be used. So that's going to leave me with 22 available letters to use. So in this first stage here, I've got 22 letters to choose from. Once I've placed a letter, I then have 21 letters left because it says 2 different letters, followed by 4 different digits. So remember that the digits are 0 through 9, so there's 10 different digits. And then once I place a digit, I would have 9, 8, and 7 remaining. If you were to type that into your calculator, the number of different license plates that you would have would be 2,328,480. That's how many different license plates are available with those restrictions. We could illustrate, anytime we could illustrate something using the fundamental counting principle, we could also write that as a permutation. So how I could show this as a permutation would be as follows. First, I need to take care of the letters. Okay, so remember when you're doing n permute r, it is how many available letters you had and how many are you permuting, how many stages. So we had 22 available letters and we are permuting 2 of them. We had 2 stages. So that would be 22 permute 2 times, right, because and we have numbers now. So then we would say, okay, we had 10 available digits that we were permuting, and we had 1, 2, 3, 4 different stages. So that would be 10 permute 4. If you typed those into your calculator, so 22 permute 2 times 10 permute 4, pause this, type it in, double check, you will get the exact same answer of 2,328,480. Let's do one last class example, and it says algebraically solve this equation here. So when it says algebraically solve an equation, we're going to be using the formula, and the formula that they gave us, I'm just going to jot it down, was n permute r, so remember you're going to get this from your formula sheet, is equal to n factorial all over n minus r factorial. Okay, so this is my n, and this is my r, right? N is equal to n minus 1, and my r is equal to 2. So putting that into this formula here, it would be n factorial, which would be n minus 1 factorial, all over n minus r. So n is n minus 1 minus r, and r is 2, factorial. That is equal to, so let's just clean this up. We've got n minus 1 factorial all over n minus 3 factorial. And that, they said, is equal to 90. I'm going to clean this up. So what we want to do is we want to simplify this. So unzip your larger factorial until we're able to cancel. My larger factorial is n minus 1, and I'm going to unzip it until I have this n minus 3. So unzipping n minus 1 would be n minus 1, n minus 2, n minus 3. If I want to stop, I've got to put factorial all over. The denominator has n minus 3 factorial, and that is equal to 90. Cancel your like terms. I'm going to simplify this by distributing. So I'm going to have, or using the distributive property, so n squared minus 2n minus 1n would be minus 3n plus 2. is equal to 90. Remember that you want to bring everything to one side, so we're going to bring everything to the left-hand side, and we're going to have n squared minus 3n minus 88 is equal to 0. You're going to find the two numbers that multiply to negative 88 and that sum to negative 3. And those two numbers are negative 11 and 8. You're going to solve for n, and you're going to get n is equal to 11 and n is equal to negative 8. One of those two numbers you would reject, and one is going to be the solution. So the solution is going to be n is equal to 11, n is equal to negative 8. This is what we reject. The reason why we reject this is because n must always belong to the element of natural numbers, so we cannot have a negative number. And then let's verify. So let's verify that n is in fact 11. So we were given originally n minus 1 permute 2 is equal to 90. If I'm verifying that n is equal to 11, I'm going to put 11 here. So that would be 11 minus 1 permute 2. That is 10 permute 2. So that would be, again, how many different ways can I permute a 10-letter word in two arrangements? Or sorry, with two stages. So two stages, 10 available letters to go there, multiplied by 9, and that is equal to 90, which is what I have right here. I'm going to give you your homework, and then I'm going to solve one more like this, just so you could see one more example of this. So for your homework, I want you to do 7, 8, 10, 11a, 14, and 15. Okay. If you're watching podcasts, which I recommend, there are 8 podcasts that you're watching for 18 minutes total. And then I'm going to do that one more example. So let's just look at this one. So it's going to say solve n permute 2 is equal to 56. So remember that the formula is going to be n permute r is equal to n factorial all over n minus r factorial. Putting this into this formula here, it would be, so that's my n and this is my r, so it would be n factorial all over n minus 2 factorial. Start unzipping. Okay, that's going to be equal to 56. And then we want to be able to unzip and we want to cancel. So I'm going to unzip the larger factorial, which is my n factorial, until I could cancel it with an n minus 2 factorial. So n factorial could be broken down into n times n minus 1 times n minus 2 factorial all over n minus 2 factorial. Cancel. Let's expand. Bring everything to the left. And we are going to factor. So the two numbers that multiply to negative 56 and that sum to negative 1 are going to be negative 8 and 7. We get two solutions. N is equal to 8. N is equal to negative 7. We only actually have one solution that's valid, which is n is equal to 8. This is the one we reject. We reject it since n must belong to the element of the natural numbers. And then I'm going to check that n is 8. Okay. So again, we were given n permute 2 is equal to 56. We're going to verify that that's 8. 8 permute 2. 8 permute 2 would be two different stages. And 8 elements or 8 letters that were available. So 8 can go in the first stage, 7 in the second stage, and 8 times 7 is 56. Or you could have broken it down, putting it into the formula, putting it into this formula using factorials. So 8 permute 2 is equal to 8 factorial all over 8 minus 2 factorial. That would be 8 factorial over 6 factorial. Unzip your 8 factorial, and you'd have 8 times 7 times 6 factorial all over 6 factorial. 8 times 7 is 56.